All right. Let's dive into Euclid's Elements. We've got some excerpts here from Heath's translation and commentary, and we're going to unpack all this.
Cool.
Yeah, we're not going to reprove all the theorems,
Right.
but think of it more like we're going back in time
Yeah.
and trying to understand, like, the historical context, the connections, the impact.
The why behind it all.
Yeah, the why.
Yeah. It's amazing how a text from over 2,000 years ago can still be relevant, right?
It really is.
It's really a testament to how powerful Euclid's approach to geometry was.
It is, and it's influenced so many people.
Oh, absolutely.
So let's start with the man himself,
Okay.
Euclid. What's so interesting is that we don't really know that much about him.
Right.
He's like this almost mythical figure.
Absolutely. It's remarkable how little we actually know about his life.
Yeah.
There's even debate about whether Euclid was one person or a group of mathematicians
Wow.
working under that name, like a pen name.
Okay, so like a team
Yeah, exactly.
under the name Euclid.
Exactly.
Okay. That makes it even more mysterious.
It does.
But there are some fun stories and myths, right?
Yes.
Like about sacrificing an ox after discovering a theorem.
Now, that story is usually attributed to Thales,
Oh, okay.
who actually predates Euclid.
Yeah.
And the story is that when he discovered that an angle in a semicircle is a right angle,
Oh, okay.
he was so excited he sacrificed an ox.
Wow. To celebrate.
To celebrate, exactly.
Okay.
But some sources actually say it was Pythagoras who made the discovery and the sacrifice.
Okay, so who knows, right?
Exactly. But either way, it shows how important those early mathematicians were.
Right, these discoveries were like
Huge.
They were a really big deal.
Okay, so before we really get into the elements,
Okay.
was this his only work?
So Euclid wasn't just a one-hit wonder.
Okay, good.
He had other works, some of which unfortunately are lost to us.
Oh, no.
But Heath mentions a few of them. He wrote things like porisms and surface loci, which showed just how much he explored in math.
Porisms, surface loci. Those sound so intriguing.
They are. What can you tell us about those?
Well, let's take porisms as an example. Based on what we know from later commentaries, they seem to have dealt with a particular type of geometric problem.
Okay.
Imagine you have a triangle, and you need to find a point inside it that's the same distance from all three sides.
Okay, yeah.
That kind of problem would be a porism.
Okay.
Sadly, though, the original text is lost.
Oh, that's too bad.
It is, because mathematicians think it probably had some really unique approaches to problem solving in geometry.
Wow, so we're missing out.
We are.
Okay. Well, even with just the elements, there's so much to talk about, right?
Oh,
So it's
yeah.
not just shapes and theorems, it's a whole system
Right.
for thinking logically and really proving things in math.
Exactly. And that system's built on some key pieces.
Mhm.
Definitions, postulates, and axioms.
Okay, those sound kind of basic, but they're really important.
They are. They're the foundation.
Yeah.
So Euclid starts by defining the simplest things. Point, line, plane.
Right.
And even these simple things caused debate, even back then.
Really?
Oh, yeah. Like his definition of a line as breathless length. Well, people questioned, like, what does that even mean about dimensions?
Wow, so even simple concepts can get pretty deep.
Absolutely. And it gets even more interesting with the postulates.
Okay, so postulates are...
These are the basic assumptions that all of Euclidean geometry is based on.
Okay.
And one of the most famous and controversial is postulate 5, the parallel postulate.
The parallel postulate. I mean, parallel lines seem pretty straightforward, right?
You'd think so. But this one caused a lot of trouble in math.
What do you mean?
Well, it states that given a line and a point not on that line, there's only one line that goes through that point and is parallel to the original line.
Okay, yeah.
And it seems obvious.
Yeah.
But for centuries, mathematicians thought they could prove it from the other postulates.
Mm-hmm.
And they all failed.
So Euclid was really onto something.
He was. And all those failed attempts to prove the parallel postulate eventually led to something amazing.
What was that?
The development of non-Euclidean geometries.
Wow. So questioning a seemingly simple assumption led to a whole new way of looking at geometry.
Exactly.
That's incredible. So we've talked about postulates, but what about proofs?
Okay.
Did Euclid just focus on shapes, or did he go beyond that?
That's where we start to see how brilliant Euclid really was.
Okay.
He goes beyond just shapes and gets into what we might call geometric algebra.
Okay, what's that?
Well, in Book 2, he uses geometric constructions to actually represent algebraic ideas, like squaring a binomial.
Whoa, wait, so he's doing algebra but with pictures.
Exactly.
That's wild.
It's pretty amazing how he managed to take these abstract ideas from algebra
Yeah.
and show them using geometric tools.
So creative.
It really highlights how connected all these different areas of math can be.
You know, I used to think about ancient mathematicians as these solitary figures just working alone on their proofs.
Yeah.
But it wasn't really like that, was it?
Not at all. They were part of a whole community. There were debates and discussions all the time.
Really? Like about math?
Oh, yeah. They argued about the best ways to do proofs, the nature of lines, even what an angle really is.
Wow, I can't imagine debating math like that.
It would have been pretty lively, I imagine. And we have records of these debates, criticisms of Euclid's work, different proofs that people proposed.
Wow.
It shows how math was a really dynamic field even back then.
That's so cool. Okay, let's talk about one of the most famous mathematical concepts ever.
Right.
The Pythagorean theorem. Every kid learns a squared plus b squared equals c squared.
Exactly.
But was Pythagoras really the first to discover it?
That's a great question. It's definitely a fundamental part of geometry.
Yeah.
But there's actually some evidence suggesting that knowledge of this relationship, or at least specific cases of it, might have existed in ancient India even before Pythagoras.
Oh, really?
Yeah.
So maybe Pythagoras just made it famous, not actually discovered it.
Yeah. That's a possibility. And what's even more interesting is that we don't have any record of how Pythagoras actually proved it.
Wow.
Assuming he did have a proof. Some historians think he might have used something called the theory of proportion.
Okay.
But there's debate about whether that was even advanced enough back then to work for this kind of proof.
Wow, so even a theorem that's so well known,
Yeah.
used by everyone, from architects to engineers,
Right.
it still has these mysteries surrounding its origins.
It does.
It makes you wonder, what other mathematical secrets are still out there?
I know. It highlights how much we still don't know about the history of math.
Yeah.
And it makes you wonder how they might have approached these problems differently if they had the tools we have today.
That's a great question. I wonder if we'll ever be able to solve all those mysteries.
It's definitely something to think about. But for now, let's keep exploring the elements and see what other insights we can find.
Sounds good. Okay, so we've talked about the big picture stuff with Euclid's elements, you know, the history, the debates, all that. But let's get into the actual content.
Sure.
What are some of the cool things we find when we actually read it?
Well, one thing that really stands out to me is how Euclid used geometric constructions
Okay.
to represent ideas that we'd now consider algebraic.
Yeah, you mentioned that earlier with book 2 and what you called geometric algebra.
Right.
I'd love to hear more about that.
So it's really clever, actually.
Okay.
Like, take book 2, proposition 4, for example.
Okay.
He shows what we know in algebra as the square of a binomial.
You mean like a
A plus B squared
right.
equals A squared plus 2AB plus B squared.
Yeah, I remember that.
But he does it all visually, using squares and rectangles.
Whoa, how does that even work?
So he takes a line segment, divides it into 2 parts,
Okay.
and then shows how the areas of the squares and rectangles you can make from those parts relate to the squares of the original segments.
So he's basically proving an algebraic identity, but with shapes.
Exactly. It's a totally different way of thinking about it.
It is. It's like instead of symbols, he's using shapes as his language.
Yeah, and it's not just about representing the algebra.
Okay.
It's also about giving a visual, intuitive way to understand it.
That makes sense.
Even today, when we think of the Pythagorean theorem, we often picture a right triangle with squares on each side.
Right.
That image really helps us grasp the relationship in a way that just the formula might not.
Yeah, it's like the geometric proof tells a story, but with shapes instead of just equations.
I like that. It's a visual story that's been passed down for centuries.
Really cool. So earlier you said that Euclid's work wasn't without its critics.
Right.
What were some of the things that people had problems with, even back then?
Well, for one, some scholars didn't like his definition of an angle.
What was his definition?
He defined it as the inclination between 2 lines.
Okay.
And they argued that it was a bit vague. Didn't really capture the essence of what an angle is.
So even these basic ideas were up for debate.
Oh, yeah. And there were also discussions about the postulates.
Right, especially that famous parallel postulate.
Exactly. Some people even tried to come up with alternative definitions for parallel lines.
Like what?
They focused on the idea of equidistance. It shows how even a foundational text, like the elements, can be interpreted in different ways.
So it wasn't like everyone just accepted everything Euclid said as the absolute truth?
No, not at all. There was a lot of discussion and reevaluation going on.
It's like Euclid's work was a starting point,
Yeah.
but it sparked centuries of further investigation.
Right. And that brings us back to the parallel postulate and how it kind of fell apart in a way.
What do you mean?
Well, as mathematicians tried to prove it from the other postulates and kept failing,
Yeah.
they started to wonder, what if it's not true?
Wait, not true. How can there be more than one line parallel to a given line through a point?
I know, it seems impossible.
It does.
But by challenging that assumption, they opened up a whole new area of math,
What area?
non-Euclidean geometries.
Oh, yeah, you mentioned those earlier. So by breaking the rules, they discovered a whole new way of looking at geometry.
Exactly.
That's amazing. And are these non-Euclidean geometries actually useful?
Oh, absolutely.
What?
They have applications in physics, cosmology, even in understanding the shape of the universe.
Wow, that's mind-blowing. So Euclid's work wasn't just important on its own.
Right.
It also led to these totally new ways of thinking about geometry.
It did. It really shows the power of questioning even the most basic assumptions.
I'm starting to see that. Okay, let's change gears a bit.
Okay.
We've been talking about the big ideas, but I'm curious about how Euclid actually structured the elements itself.
Well, one of the most remarkable things about it is its organization.
How so?
It's not just a random bunch of facts.
Right.
He carefully arranged all the propositions, the
Propositions.
statements and proofs,
Okay.
starting with the simple definitions and postulates,
Yeah.
and then building up to more and more complex theorems.
So it's like he's taking you on a journey through geometry.
Exactly.
They make sure you understand each step before moving on.
Right. That emphasis on logic and clarity set the standard for math writing for centuries.
Wow, so the way we learn and write about math today is still influenced by Euclid.
To a large extent, yes.
That's incredible. It's amazing to think about how a book written so long ago can still be so relevant.
It is. But it's also important to remember that the elements we have today isn't exactly the same as what Euclid wrote.
Oh, right. You mentioned earlier that there were parts added later by other mathematicians.
Right, the interpolations.
Yeah, what's the story there? Why did they add stuff?
Well, it's hard to say for sure, but some of it might have been to clarify things.
Okay.
Over centuries of copying and translating, some parts could have become unclear.
So they were trying to help?
Possibly. But some additions might have been attempts to, expand on Euclid's work,
Okay.
to answer questions he didn't address.
That makes sense. He couldn't have thought of everything.
Right. And there's one example that's particularly interesting.
What's that?
It's a proposition at the end of Book X, dealing with the incommensurability of the diameter and side of a square.
Incommensurability? What does that even mean?
It's basically about irrational numbers.
Oh,
Numbers you can't express as a simple fraction.
right.
And this proposition, it doesn't really fit with the rest of Book X.
Why not?
Well, Book X mostly focuses on classifying different types of incommensurable magnitudes.
Okay, hold on. What are incommensurable magnitudes again?
It's a pretty cool idea that fascinated the ancient Greeks.
Okay.
Two magnitudes are incommensurable if you can't measure both of them perfectly using the same unit. Like, think about the diagonal of a square and its side.
Yeah.
You can't express the diagonal as a simple ratio of whole numbers compared to the side.
Ah, I see.
This discovery of irrational numbers was a big deal for them.
It must have been. Okay, so this extra proposition about irrational numbers.
Right.
It sounds like someone just stuck it in there, even though it wasn't part of Euclid's original plan.
Exactly.
Yeah.
And it shows how challenging it can be to preserve and transmit knowledge over time.
Yeah, I guess the elements we have today is a mix of the original and all these later changes.
It is. It's like a tapestry woven from different threads.
Wow, that's a great analogy. Makes you wonder what other surprises are hidden in there.
I know, right? That's what makes studying these ancient texts so fascinating.
I'm definitely feeling inspired to delve deeper into the elements after all this.
That's great. It's truly a remarkable work with so much to offer.
Man, there's so much in Euclid's elements, it's kind of overwhelming.
It's true. There's a ton of info there.
We've talked about all these definitions, postulates, proofs. It's a whole system, right?
It really is a system.
Yeah.
And that's actually a big reason why it's had such a lasting impact,
Oh, you mean like how it's organized?
Exactly. It's not just a jumble of facts. It's a very carefully built structure.
Right, right.
Euclid starts with those basic building blocks, the definitions and postulates.
Yeah.
And then he, step by step, leads you through to those more complex theorems.
So each thing builds on the one before it.
Exactly. It creates this incredibly logical flow. You understand each piece before moving on.
That's smart.
It's brilliant. And that approach, that focus on logic and being clear, it set the standard for how people wrote about math for centuries.
Wow. So like even today, how we learn math is still influenced by Euclid.
Oh, absolutely.
Yeah.
It's no exaggeration to say that the elements shaped how we think about teaching and presenting math.
That's amazing. It's really mind-blowing how influential something written over 2,000 years ago can still be.
It really is. But, it's also important to remember that the elements isn't just some ancient relic.
Okay.
It's full of insights and challenges that we can still engage with today.
I see what you mean. We keep talking about the impact of the elements as a whole,
Yeah.
but it's interesting that it wasn't always this fixed thing, right? You
Wow.
mentioned those additions, the interpolations, made by other mathematicians.
Okay.
Do we know why they added stuff? Were they trying to, improve on Euclid or maybe even disagree with him?
That's a great question. It's possible some were just trying to clarify things.
Okay.
After centuries of copying and translating, some parts might have gotten confusing.
So they were trying to make it easier to understand.
Maybe. But others might have been trying to add to it.
To add to it.
Yeah, like explore questions Euclid didn't get to.
That makes sense. I mean, as smart as he was, he couldn't have thought of everything.
Exactly. It's kind of like how scientists today build on the work of people who came before them.
I see. So taking those old ideas and seeing what else you can do with them.
Exactly. Just like how we talked about challenging the parallel postulate, leading to new types of geometry.
Right. Pushing the boundaries and seeing what happens.
It all comes back to that curiosity, to that willingness to question things.
And to explore.
Yes. And in a way, the elements, even with all its changes, embodies that spirit. It shows us that math isn't just a set of rules. It's a process.
A process of discovery.
Exactly. And of debate, too.
Oh, wow. I have to say, this whole deep dive has changed how I think about Euclid in the Elements. It's not just some old textbook.
It's much more than that, right?
Yeah. It's like proof that humans can think logically, and it's beautiful.
It's a testament to the power of human reason. And this is just the beginning, really.
What do you mean?
The Elements opens up this whole world of geometric wonder.
Oh, I like that.
There are so many connections to explore, patterns to find, new things to learn.
It's kind of like how Euclid started with simple things and built up to those complicated theorems.
Exactly. We've got a taste of the foundations, and now who knows where this knowledge can lead us.
That's exciting. So keep exploring, keep asking questions, and most importantly, never lose that sense of wonder.
I love that.
You never know what mathematical treasures you might find. Well, that's all the time we have for this deep dive into Euclid's Elements. We hope you've enjoyed it.
And maybe even learned a little something.
We hope it's made you curious and you see the world a little differently now.
Thanks for joining us.
Until next time.